Okay, I'll get started. Hope you can hear me okay. In the beginning of the course, we started talking about electrical forces. We moved on to talking about electrical fields as the mediators or the carriers or conveyors of electrical forces. We moved on and talked about electrical flux and that positive, negative charges are kind of the source and drains or source and sinks of electrical flux. And then in today's class, we're going to introduce one more concept, one additional concept. It's electrical potential. And that's related to electrical energy. So after today's class, we really stepped through the key components of understanding electrical interactions, from electrical forces to electrical fields to electrical flux, and in today's class, electrical potential. So that's the plan. Okay, so here's a list of the objectives for today's class, or the content of today's class. Firstly, I want to step back to something that you would have done in first semester general physics, and that's to consider two perspectives on how things work: the energy and force perspectives on how things work. And we're going to think about the energy and force perspectives on how things work for gravity, something we've talked about in the past, and how things work for electricity, something that we're going to talk about now. So that's the first item. Through that, we're going to introduce the concept of electrical potential, and we're going to define carefully the electrical potential, and we give it the symbol V. We're going to look at how the electrical potential V is connected, related to the electrical field E. We'll look, for example, how to calculate the potential from the field, or how to calculate the field from the potential, those two cases. I'm going to show you some examples and illustrations of electrical potentials and electrical energy, and we'll work some problems, examples on electrical potential and electrical energy. And at the end, I'll say a few words about conductors and electrical potentials and electrical fields and electrical charges. So that's the overall plan, if I can do that. Okay. Why there is a spider's web on this overhead will become clearer later on. But for now, why there's a spider's web on the overhead is a mystery. So I want to talk about this idea of two ways of thinking about nature: force perspective and energy perspective. I want to remind you really of these two ways of thinking about nature: force perspective and energy perspective. So here's how we introduced the energy perspective from an understanding of the force perspective. The idea is that when forces act, when you apply a force, those forces do work. And that doing work is the transfer of energy, the flow of energy. And that's how we expose, from thinking about the forces acting, that's how we expose the energy being transferred. So the key idea is that forces do work, forces transfer energy. And that's what's shown in this little overhead here. Here I am, I've got my crowbar, I'm lifting the floorboards, and from the force perspective, here I am applying a force. That force on the top right end of the crowbar is exerting this force down here on the uh, bottom left of the crowbar. From the energy's perspective, I'm doing work on the crowbar. I'm transferring energy to the crowbar on the top right end of the crowbar. And the crowbar is transferring energy to the floorboard on the bottom left end of the crowbar here. So I'm applying a force, inputting energy, doing work. The crowbar is applying a force. It's outputting energy. It's doing work. And those are two ways of viewing what's going on here. And both ways are useful. Sometimes one more useful than the other, sometimes the other more useful than the first. Okay. So here's an old slide I had. I wanted to recycle it. And then I'm going to recycle it into a new slide, the next slide. So we'll see it again. But this is an example where we've got an object, it's an apple, and it's been dropped. It's falling towards the ground. And in this little sketch, that apple with some mass m is falling to ground under gravity from that upper point A, here it is, to this lower point B. And so there's two ways of thinking about this. There's a force perspective way of thinking about it. So the apple is immersed in a gravitational field, and that's what I've pictured with these field lines. Here's the gravitational field. It experiences a gravitational force in proportion to the field, and it accelerates downwards under the action of that force. And so that would be a force perspective on what's going on. The second way of thinking about this situation is from the energy perspective. The apple at the initial position here has some gravitational energy. As it falls towards B, it's releasing that gravitational energy. It's giving up that gravitational energy. And that energy is going into the accumulating kinetic energy. The gravitational potential energy is transformed into kinetic energy of the falling apple. So from that perspective, we could imagine these, look at these two little piggy banks. I'm very proud of this picture. This is the gravitational potential energy piggy bank for the falling apple. This is the kinetic energy piggy bank for the falling apple. From the energy perspective, from the work perspective, as the apple falls, the energy in the kinetic gravitational potential energy piggy bank is decreasing. There's less joules of gravitational potential energy stored. The energy in the kinetic energy, moving energy piggy bank, that's increasing. There's more joules of kinetic energy. We're transferring energy, and that's doing work. The gravitational force here is doing work and moving that energy. And so those are two ways of thinking about the falling apple, from a force perspective and the action of the gravitational field and the gravitational force, from the energy perspective and the gravitational potential energy and the kinetic energy and the work done transferring energy from potential to kinetic energy. Well, here's the same thing, but not in the context of gravity, rather in the context of electricity. So instead of a apple of mass m falling under gravity, this is a apple of charge q that's falling under electricity. And so upstairs here, this is the charged apple, charge q, at some initial location. It falls down here to some final location. So it falls from A to B. Oh, No lecture classes without me accidentally changing slides at least once, and I'm sure there'll be several times. The apple falls from A to B. The charged apple falls from A to B. This time, no, is falling under the influence of an electrical field. It's immersed in an electrical field, not a gravitational field. And it experiences electrical force in that electrical field in proportion to that electrical field, rather than experiencing the gravitational force that was proportional to the gravitational field. And that force causes it to accelerate downwards, undergo an electrical acceleration downwards from the initial location A to the final location B. And that's the force perspective of the falling charge. But we can also think about an energy perspective of the falling charge. Initially, the charge in the electric field has some initial stored electrical potential energy. As it falls, it gives up, it releases that electrical potential energy, and it turns that electrical potential energy into kinetic, moving energy as it's falling. So again, I pictured that with this very clever diagram of the piggy banks of energy. As the apple falls, its electrical potential energy is decreasing. The energy in this piggy bank corresponding to electrical potential energy is decreasing. The energy associated with motion, kinetic energy, that's increasing, correspondingly increasing. And that's this piggy bank here associated with kinetic energy. And that transfer of energy, that flow of energy from potential to kinetic energy is through the work done by, this time, the electrical force rather than the gravitational force. And so that's the energy perspective. And just like when we thought about gravity, force perspectives, energy perspectives, gravitational forces, gravitational potential energy were both useful concepts. In the electrical case, electrical forces and electrical potential energy are also, they're both useful concepts in understanding physics problems. And they both, the gravitational case, the electrical case, they both fit into this sort of big picture of our energy perspective of the physics world. So this slide is the greatest of slides because it sort of describes the whole of physics, 211, 213, which involves gravity and electricity. In one super slide, it shows us a world that's full of energy. It shows us that there is electrical potential energy. That's over there on the top left. There's gravitational potential energy in this piggy bank over here on the top right. And there's energy of motion, kinetic energy. It's the piggy bank at the bottom. And energy in our universe full of gravity and electricity and motion is flowing, is being transferred between these different piggy banks, between these different forms by the action of the gravitational forces, the electrical forces. But overall, and this is the usefulness of this picture, the total energy in our universe, so that's the sum of the gravitational potential energy piggy bank, the electrical potential energy piggy bank, and the kinetic moving energy piggy bank, that total energy is conserved. So we can move energy around. We can shift energy around from one form to another, from one owner to another owner, but we never ever destroy energy. We never ever create new energy. This equation here says that the total energy in all its kinetic and potential forms initially is the same as the total energy in all its kinetic and potential energy forms at the end. Okay, I want to demonstrate to you that, my claim that there's electrical energy, like my claim that there's gravitational energy, is true. And I'm going to show you a demonstration that it's true. But actually this picture, this overhead, is a picture showing you that it's true. Let me first explain this picture, and then I'll show you the demonstration. This is a picture in which there are overhead power lines that bring electricity to all of our houses, right? Overhead power lines in this picture. So at the top of the picture, you can just see these power lines. Here they are. Just so you know where they are. Surrounding these power lines carrying electricity, surrounding those power lines is electrical fields. And actually strong electrical fields surround overhead power lines carrying large electrical currents. These white lights standing vertically are just fluorescent light tubes. And you know, you're used to seeing these. Maybe you've got one in the ceiling of your kitchen or in your bathroom, or you certainly see them in work settings, these fluorescent light tubes. If you go in Walmart, you'll see thousands of them, in Target, thousands of them. But these fluorescent light tubes are not connected to electrical circuits. They're not hooked up to electrical circuits. They're just stuck in the ground. They're just planted in the ground. But still they're lit, still they're shining. And they're lit and shining because they are immersed in the electrical field of the power lines. And that electrical field of the power lines contains electrical energy. And we're seeing through the light, through the white light, fluorescent lamps, we're seeing that electrical energy in those electrical fields. And so that's a demonstration that whilst we cannot see the electrical fields of the electric power lines, we can see that they contain electrical energy within inside those electrical fields. Now I'm going to show you a demonstration of this. Let me stop sharing this guy. So maybe you can see me now. This is a small fluorescent light tube. So, you know, in Walmart and Kmart, you see the big fluorescent light tubes. I've just got a small one. I've got it on an insulating handle. So that's important for my safety. I got another light here. This is a different type of fluorescent light tube. It's a nitrogen light tube here. Again, I've got it on, this is just in brown here, this is just a handle for my personal safety in this dangerous demonstration. Okay, so those are the tools you're going to see. Now I'm going to share the video of the demonstration. Okay, so I hope you can see this little video here. Now what you're seeing in the picture over here on the right, that's the Van de Graaff generator. Remember I think it was probably the first or second class, I introduced the Van de Graaff generator. It was this device that was invented to accumulate electrical charge. And I'm going to switch it on in this video. Accumulate electrical charge. Surrounding it, we now know, is this electrical field. And you can create and accumulate a lot of electrical charge in a Van de Graaff. And you can create a larger electrical field in the regions surrounding the Van de Graaff. What I'm going to then do is take those two fluorescent bulbs, or two fluorescent lamps that I showed you, and I'm going to put them in the neighborhood, put them nearby the Van de Graaff generator. When it's running with the electrical field, you're going to see them glow. And so let's go ahead and do that. So this is the Walmart Target version of the fluorescent lamps, and I didn't do a great job that time, but I think I'm going to come back and do a little bit. Look at that. See those colors burst out when I catch it right? That's just seeing the energy. I'm not touching it, I'm just seeing the energy that's literally stored in the electrical field. And here we go again. You're seeing the energy that's stored in that electrical field. I'm personally impressed by that. Okay, then I'm going to get the other lamp. I think I tripped over somewhere in there. I'm getting up because I had to switch all the lights off. But then I'm back here with the other lamp, and I'm putting it in the neighborhood of the Van de Graaff in that region of electrical field, and you see it glow like that, showing you that there is energy in that electrical field. It's a really great demonstration. I think that's it. Okay, well, I hope you like that one. I was particularly proud of the lighting that I did for that. So I'm gonna remember that demonstration. Okay, so I want to go back to sharing my slides if I'm capable of that. Which right now I'm not sure I am. Okay, so I hope you can see my slides. Maybe I'll just stop for a moment. Any questions on that? So those few slides and that demonstration are just to convince you that that energy perspective that we use for gravitational interactions, we can use that energy perspective for electrical interactions too. Okay, so no questions means one of two things. You probably know this. It means that I was incredibly clear, or it means the alternative is that incredibly clear means you got no questions to ask. I've just explained it all. Or that I was incredibly unclear, in which case you can't even think of a question to ask. It was so unclear. So it's one of those two. Okay, so now I want to introduce this new quantity we call the electrical potential. We give it the symbols V. And when I introduce it, I'm just going to recall this older quantity, the electrical field E, and how we define that. Okay. I'm just getting my pen working again. Here was how we define the electrical field. If you remember, what we did was we imagined a source charge or charges that created an electrical field. And then we imagined a test charge that we placed in that electrical field. And by measuring the force on the test charge, we were able to infer the field at the location of the test charge. And so that's what you see here. Here's the test charge, Q. Here's the, sorry, this is the source charge, Q. Here's the test charge, Q naught. And the electrical field at the location of Q naught, I've got to correct this. The electrical field is the force experienced by Q naught divided by its charge. And so that's kind of how we probe or explore or we measure the electrical field of that location with the test charge. It's just a tool, it's just an instrument, it's just a probe for measuring this sort of abstract electrical field. So hopefully that was a reminder. So now I want to introduce how the electrical potential. And again, we use the concept of a source charge and a test charge. So again, I'm imagining some source charge, we're calling it Q. might be a single charge, or it might be just a distribution charge, but now it's not only producing the electrical field, but it's producing the electrical potential. I've just seen a question. I'm sorry if there's no question is stupid. I should say that first of all. If this is a stupid question, but get how running electricity causes fields, but why is that? Why did the power lines cause fields? Well, that's actually a good question because I didn't really explain why the power lines cause fields. And actually that's a topic we're going to return to later on in the course, why power lines create electrical fields. So I will explain it in detail later on in the course, but for now, just believe me that if you're in the neighborhood of a power line, you're immersed in actually electromagnetic fields. And they're actually oscillating, vibrating electromagnetic fields. But there is electromagnetic fields surrounding power lines. If you're a conspiracy theory person, I know a few of them, then, you know, this is one of the things you worry about, the power lines are immersing us in electric and magnetic fields. Well, lots of things immerse us in electric and magnetic fields. There's nothing to worry about, but they do produce electric and magnetic fields. So good question. Okay, let's get back to defining the electrical potential. Here's our source charge. It creates an electrical field around it. And now I'm saying it also creates an electrical potential around it. Here's our test charge, Q naught. This is how we probe the electrical field, how we're going to now probe the electrical potential. So the way we think of it in this case is that the source charge Q is producing a surrounding electrical potential V. And then the two charges together, the interaction of those two charges, the source charge and the test charge, has some associated electrical potential energy. And it's in terms of that electrical potential energy rather than in terms of the electrical force that we define the potential. Anyway, so here's how we define the potential. The potential, and it's actually strictly the potential difference. I'll say more about this in a moment, but the potential is the work that is done. So the energy that you have that is transferred when you carry this test charge in towards the source charge, divided by the amount of charge that the test charge has. So that defines this electrical potential. It's also the change in potential energy of this system of charges when you walk this test charge in from far away. It's how much the electrical potential energy changes divided by the amount of charge of the test charge. So again, if you want to think about what the test charge is, it's kind of the probe that allows us to measure the potential. It's the tool or the instrument that allows us to measure the potential, just like in the case of the measuring the electrical field or inferring the electrical field. In both cases, right, let me be clear that electrical potential, electrical fields are kind of abstract quantities. You know, you can't see the field, you can't see the potential. They're abstract quantities. This relates those abstract quantities of the electrical potential, electrical field to much more concrete quantities. You're measuring the forces, or you're measuring the work you've done on the test charge. And that's a measurable thing. That's a much more concrete thing. Okay, I want to mention one subtlety. That's why the skull and crossbones are here. So there's one important subtlety about electrical potential versus electrical field. With electrical field, when we quote an electrical field, and when we say that the electrical field is 1 Newton per Coulomb or 10 Newtons per Coulomb, it's the electrical field at a point in space, a particular point in space. And that will determine the force on a charge at that point in space. When we talk about electrical potential, The only thing that's actually significant, physically measurable about electrical potential is that what we call this potential difference. It's the difference in potentials between two different points in space. So in the last slide, when I walked the test charge in towards the source charge, I measured the amount of work that I did on the test charge. I measured the change in electrical energy of the charge arrangement. So it was a difference between when the test charge was far away and when the test charge was in the neighborhood of the source charge. Only that potential difference is physically significant. We can only observe, measure, determine potential differences. Unlike fields where you could say the field is this or the field is that at a particular point. So I hope that's a little bit clear. Okay, so now I want to turn to, now we've introduced the electrical potential. We previously defined the electrical field. Let's look at some examples, illustrations of relationships between the electrical potential, the new guy, and the electrical field, the old guy. Okay, so this slide shows us it's about the relationship between the electrical potential and the electrical field. Specifically, this slide tells you how to calculate an electrical potential difference. I call it delta V upstairs here from an electrical field. And I'm going to illustrate it, I'm going to ask you to imagine this situation that I pictured here. So in this situation, I've got over here on the left is some positively charged plate. Over here on the right is some negatively charged plate. Field lines emerge from the positive charges on the left. Field lines end on the negative charges on the right. So the positive charges over here on the left act as a source of the field lines, source of electric flux. The negative charges over here on the right act as the sink or the drain of the field lines, the end of the negative of the electrical flux. And actually this particular arrangement of a uniform positively charged sheet on the left, a uniform negatively charged sheet on the right, that produces a nice uniform electrical field. Look, the field lines are equally spaced and just run from left to right across the slide. So the two plates have made a region of uniform electrical field. I've explained how I made that field, and I just called it E here. I placed a positive charge in that field, and that positive charge, its initial location is xi, the initial position, and I've allowed it to move, and here's its final location, xf. That's the final location, and the displacement of the positive charge as it moved from left near the positive plate to right near the negative plate is that displacement delta x is the difference between the final position xf, the initial position xy. Okay, so I'm going to derive in these two steps here, one step really, the relationship between the electrical field that the charge moved in and the change in potential when the charge has moved. So we want to find out what delta V is, the change in potential, the potential difference when the charge moved from the left to the right. And the way I'm going to do it is this relationship here. This relationship here is that link between the force and energy perspective. The change in potential energy, so that's over here on changing electrical potential energy, is the negative product of the force and the displacement. So that's the relationship between work and forces, between energy transfer and forces. Well, changing potential energy, changing electrical potential energy, we can rewrite that using our definition of the potential, rewrite it in terms of the potential. The electrical force over here, we can rewrite that in terms of electrical field. And if you do that and cancel out the Q's, then you get this little relationship here. And this little relationship here tells you the connection between the change in potential when we move the charge and the field that the charge was moved through. And the change in potential, delta V, is simply the field times the negative displacement that we move the charge through. And so that's the simple relationship between electrical potential difference and electrical field E. I should say that this particular relationship applies if you've got uniform fields. And this is an example of a uniform field. You cannot apply this relationship if you've got non-uniform fields. The examples that you'll meet for using this relationship are the cases where you've got a uniform field. And so that's an example of how you could calculate, how you might calculate the potential difference knowing the electrical field. Oh. Here's a slide about doing the reverse, calculating the electrical field, knowing the potential difference between two locations in space. In this particular slide, if you look at it, it's a graph. Let me make it clear what it is. Horizontally, this is position. So imagine an x-axis, right? And we're counting out centimeters along the x-axis. We're walking 1 centimeter, 2 centimeters, 3 centimeters, 4 centimeters, 5 centimeters along the x-axis. And what we're plotting vertically here, this is the electrical potential as we walk up and down the x-axis. And we see as we walk from the origin to 1 centimeter, the potential goes from 0 to 30 volts. As we walk from 1 centimeters to 2 centimeters, it goes from 30 volts to 0 volts. As we walk from 2 centimeters to 3 centimeters, it's constant, 0 volts, the potential. As we walk from 3 to 4 centimeters, it goes down to minus 30 volts. And finally, as we walk back to up to 5 centimeters, from 4 centimeters, it goes back to 0 volts. So that's a map. That's a diagram, a drawing of the electrical potential in some region of space. So you can look at that map. You can inquire at that map. Well, what's the underlying electrical field that's related to the potential? All you have to do is turn around the equation from the last overhead. Remember that said that delta V equals minus E times delta X. Well, that infers that E is equal to minus delta V over delta X. So if you know the change in electrical potential between two locations, and you know the displacement between the two locations, divide one by the other, take the negative that's going to give you the electrical field here. So for example, let me just work a couple of examples here. Supposing we go from the origin to 1 centimeter. The change in potential, the potential difference, is the final minus the initial potential. So that's 30 volts. The displacement is the final position minus the initial position. So that's 1 centimeter. So the electrical field is minus the change in potential, 30 volts, divided by the change in position, 1 centimeter. That's going to be minus 30 volts per centimeter. So that's the corresponding electrical field in this region between 0 and 1 centimeters. Between 1 and 2 centimeters. Well, as we walk from the 1 centimeter post to the 2 centimeter post, the voltage, the potential changes from 30 volts down to 0 volts. So the initial voltage is 0. Sorry, the final voltage is 0 now. The initial voltage was 30 volts. So the change is minus 30 volts. The displacement is 1 centimeter again, final position minus initial position. That's 1 centimeter displacement. And so here the electrical field is minus 30 volts divided by 1 centimeter. So that's going to be plus 30 volts per centimeter. So the electrical fields in the region, the first centimeter, and in the second centimeter, they're the same strength, but they're the opposite direction. In this region here, from 2 centimeters to 3 centimeters, well, what's the field there? Well, the field is, again, given by this equation, is the change in voltage. So it's 0 volts minus 0 volts, which is 0 volts, divided by the displacement. That's 1 centimeter. So that's actually an electrical field that's 0. And so that's how you would calculate that. And so that's the relationship between the voltage and the field. If you know the potential difference and you want the field, how you would calculate the field. Okay, let's do a quiz question then on this topic. This quiz question is about the relationship between potential and field. And the questions in the chat were about the relationship between potential and field. So let me just summarize that our last 2 slides introduced 2 equations. I'm going to write them down here, which are really one equation rearranged, that are a recipe for calculating the potential difference between 2 points in space in terms of the electrical field in that region of space, or calculating the electrical field in a region of space from the potential difference between 2 points in space. So these 2 equations here. Now, there's an important point in here. There's a minus sign. Why is there a minus sign? In a sense, the minus sign is a convention about how we define energy, potential energy, stored potential energy. So when we define the stored potential energy, there's a negative sign in that equation defining the stored potential energy. And that's a convention. And these minus signs here are a result of that convention. It means that the electrical field here is the negative slope of the electrical potential. The electrical potential is the negative product of the field and displacement. And it is all about a convention, and we're stuck with this convention, and there's pros and cons of this convention, but here it becomes a negative sign. But anyway, with these equations, let's answer the question. What is the electrical field in this region here between 3 and 4 centimeters? Well, what that electrical field was the change in voltage. Now remember, that's always the final voltage minus the initial voltage. So it's minus 30 minus 0 volts divided by the displacement. So that's 4 minus 3 centimeters. And so we end up with 30 over 1 So this is plus 30 volts per centimeter. For the second step, this was the first step going here, the second step going from 4 to 5. Again, use the same equation, relationship between electric field and potential. The initial potential is now minus 30 volts. The final one is 0 volts. So this becomes 0 minus 30. 0 minus minus 30, sorry. The change in position is the final position minus the initial position. So it's 5 centimeters minus 4 centimeters. And so here we end up with minus 30 in the numerator, 1 centimeter in the denominator. We end up with minus 30 volts per centimeter. So again, in these two regions here, the field strength was the same size, but it was opposite directions in those regions. So I hope that's clear. Okay, now I want to show you another equation is the equation for the electrical potential of a point charge. Now I also want to show you some ways that we sketch or draw electrical potentials and how that's related to how we sketched or drew an electrical field. So that's the next few slides on here. Okay, this slide, what do we have here? Here we are. Start again. What do we have here? We have a graph or a plot of something that's familiar, the electrical field of a point charge, its strength, and something that's new, the electrical potential of a point charge. So in this sketch here, horizontal axis, that's the distance from the location of the point charge. So let's imagine the point charge is at the origin here, and here we're 2 meters, 4 meters, 6 meters from the point charge. And then vertically, what are we plotting? Vertically, what we're plotting is either the electrical field strength, so the red curve is the electrical field strength, or the electrical potential. The blue curve is the electrical potential. Now, this equation for the electrical field strength we met earlier. It says that the electrical field that surrounds a point charge has a strength, a size, magnitude that is in proportion to the amount of charge. So more charge, more field, and inverse proportion to the square of the distance from the charge. So if you double the distance from the charge, then you actually quarter the field strength. And then there's this Coulomb constant that sets the scale of the electrical field. So that's an old equation, and we're just seeing what it looks like on a graph. The red curve is, you know, that 1 over r squared dependence, that inverse square law dependence. What's new here, so this is a new friend. Like we got the old friend, the equation for the strength of the electric field. With a new friend, it's equation for the strength of electrical potential. The electrical potential is in proportion to the charge again. So again, just like the electric field, more charge, more potential. And just like electrical field, less charge, less potential. But it doesn't fall off as the square of the distance. It just falls off as the inverse of the distance. So you see that the field in red falls off much more quickly, 1 over r squared, 1 over the square of the distance. The potential in blue falls off less quickly, falls off as 1 over r, the inverse of the distance. And actually, although I'm not proving this in any way, this potential is this field, the field is the negative slope of the potential. So remember that the field is the negative change in potential divided by change in position. That means that's the negative field is the negative slope of the potential. And so when you look at the field, it's really just a sketch of the slope of the potential. And where the potential has a steep slope, that's where you get a strong field. Where it has a gradual slope, that's where you get a weak field. Okay, so the reason to know these two equations, the field of a point charge and the potential of a point charge, is really because those are building blocks for figuring the fields and potentials when you have, say 2-point charges or 3-point charges or more point charges or distributions of charge. So they're building blocks of more complicated of calculating the fields of potentials in more complicated situations. So that's why we introduce those. Okay, this is just to show you another way of thinking about or picturing or viewing the electrical potential of a point charge. So here I'm imagining in the center of this plot, this is a positive charge. I've done it again. This is a positive point charge here. And this is just a sketch, color-coded sketch of the potential, electrical potential in volts that surrounds that charge. So up here in red, the potential is large. And down here in blue, the potential is getting much smaller. You see the scale here, 0 volts, 1 volts, 2 volts. And so this is just the plot of, KQ over R. And you see that if you were to if you imagine a charge, imagine you got a little charge in your hand, a little puppy in your hand or whatever, not puppy, I don't know, a little ant in your hand. But imagine it's a little charge in your hand. Surrounding that charge is a potential. That potential, if it's a positive charge, is a strong potential when you're really close to the charge, but then falls off to be a weak potential as you get further from the charge. Now, importantly, the electrical potential has just the size, just the magnitude. Remember, the electrical field also had a direction, an orientation, but the electrical potential has just a size, just a strength, just a magnitude. Here's another way that we often draw potentials. And this is how it's related to how we draw fields. So again, this is another drawing of a point charge, positive point charge at the center here, Q. I've sketched around it, right, the familiar electrical field lines. I mean, I say I sketched. Obviously, I didn't sketch this. I stole it from the textbook. Here are the field lines. They tell us the field is strong in the neighborhood of the charge. They tell us that the field is weak far from the charge, where the field lines are closely packed, where the field lines are loosely packed. They tell us the direction of the field. It's going to the left on the left, it's going to the right on the right, up upstairs and down downstairs. So that's that field and how we sketch that field. And then these contours, these dashed lines, I call them contours. These are called equipotential surfaces. Everywhere on this contour is at the same electrical potential, and they form concentric shells around the positive charge, concentric shells of constant electrical potential. And so this shell might be 1 volt, this might be 2 volt, this might be 3 volt, this might be 4 volts. as given by this equation for the electrical potential. And so when we draw fields, we use field lines because that's a way of conveying both the strength and also conveying the orientation, the direction. When we draw potentials, we just need to convey the size of the potential. So we draw these contours of equipotential, 4 volts, 3 volts, 2 volts, 1 volts. Now, when the potentials are closely spaced, so they're closely spaced here, right? That's where the potential is changing a lot. So its slope is large, so the field is strong. When the potential is changing more slowly out here, that's where the slope of the potential is shallow and where the field is weak. And so you see also, not only, I mean, it's a beautiful picture, it's a beautiful bit of art, really. I mean, kind of. It's the field lines convey the electrical field to us. The contours convey the electrical potential to us, and together they convey the relationship, the connection between these abstract potentials and fields. So it's a nice picture. Okay, want to sketch one more electrical field, electrical potential combination. And this is for a charge distribution we mentioned a class or two ago. It's the electrical charge arrangement is called the electrical dipole. It's a charge arrangement where you've got two equal-sized, oppositely signed charges in proximity, but separated. And you know, we always say this is the classic example of an electrical dipole in physics and chemistry. It's the water molecule. I mentioned this before. The water molecule has a positive and negative end, head and tail. And it's that fact that it is a big electrical dipole actually gives rise to its important properties. It being a liquid, it being a solvent, and it gives rise to cells and life. So, you know, tonight you might want to thank the water molecule for being an electrical dipole, because if the water molecule wasn't an electrical dipole, then you and I wouldn't be around. We have to thank it for being this big, strong dipole. Anyway, getting off a tangent there a little bit, I think. I wanted to show you this sketch. This is this one, I would like to have a nice poster of this on my, I don't know, my bedroom or kitchen wall or something like that, because I think it's really it's a nice little piece of art involving field lines and involving equipotential surfaces. And it's the field lines and equipotential surfaces of a electrical dipole, of a water molecule. So not only is it a nice piece of art, but it's a really important piece of art. Okay, we got a positive charge here. Oh, crap. Got a positive charge here. And we got a negative charge here. So these are the two ends of the water molecule, and they're separated by some distance. And that's what an electrical dipole is. Out of the positive charge comes electric flux, comes field lines. We've talked about that. And you see these lines coming out of the positive charge in orange here. These are the field lines coming out. Over here on the negative charge, that's the end, the drain of flux or the field lines. You see the field lines disappearing into the negative charge. In the neighborhood of the positive charge, right, if you're close up in here, it just looks like field lines coming radially outwards because you're close to one charge and far from the other one. So here it looks just like the field of a positive charge. In the neighborhood of the negative charge, it looks just like the field of a negative charge because you're so close to the negative charge compared to the positive charge. But in between, say here, or over here on the left, over here on the right, upstairs, downstairs, you get that characteristic pattern of the field lines of an electrical dipole. And that characteristic pattern has that characteristic that the field is not falling off as 1 over r squared, the inverse square of the distance, but 1 over r cubed, the inverse cube of the distance. So all that's embodied in this picture. Added to this picture are contours of electrical potential. So here's one. Maybe that's 3 volts. Here's another one. Maybe that's 2 volts. Here's another one. Maybe this is 3 volts, 1 volt. These are contours of constant electrical potential. Anywhere, if you imagine you're an ant, you walk around those dashed lines, you're at constant electrical potential. If you walk off them, then you're starting to walk up the electrical potential hill or down the potential hill. Same thing over here. These are contours of electrical potential. These might be minus 3 volts because you're near the negative charge, minus 2 volts, minus 1 volt. And so that's what the electrical potential looks like. I'll show you on the next slide an alternative way of drawing the potential. And it's here. So this is a more sort of three-dimensionally-ish picture of the electrical potential surrounding the dipole. Here's the positive charge. Oh, crap again. Here's the positive charge on the top of this mountain. Here's the negative charge at the bottom of this well. So near those charges, you're going to get really large positive or really large negative electrical potentials. So it's a very funny world or contour here. You've got this steep mountain over here on the left with the positive charge. You've got this deep valley over here on the right with a negative charge. And then you've got this weird kind of plateau in between where there's just the gradually varying electrical potential and a gradually varying a small electrical field. And so that's the second way that you can draw the electrical potential of an electrical dipole. Okay, want to look at a final example, I think. I want to calculate the I want to consider this arrangement of charges. We got a charge, positive charge of 5 nanocoulombs here, Q1, and a negative charge, minus 3 nanocoulombs here. And we're placing them in space at a separation of 0.35 meters. So here's the positive charge, here's the negative charge, here's the separation of 0.35 meters. This is just the midpoint. And we're asked 2 questions. We're asked, what is the potential at the midpoint between the charges? And what is the potential energy, the entire arrangement of 2 charges? So this is a question about electrical potential at this location here, and the electrical potential energy stored by this entire arrangement here. And so on the next 2 slides, let's see if we can answer these 2 questions. Firstly, let's see if we can calculate the potential at the midpoint, knowing the electrical potential of a point charge and superimposing the electrical potentials of these 2-point charges. Okay, so this is my calculation of the potential at the midpoint. So right here, what's the potential here? Well, the potential at this location, the electrical potential at this location, we're just going to call it V. It's the sum, it's the superposition of the potential due to this charge and the potential due to this charge. This should be Q2, sorry. So I'm going to call those V1 and V2. And the potential due to charge Q1 is just given, because point charge, just given by that expression that we met, KQ over R, where R is the distance from the charge to the field point. And the potential due to the second charge, again, that's just given by that expression for a point charge, KQ over R, where here this R is the distance, again, from the charge to the field point. Well, given this little expression that is really just based on two things, the idea that we can superimpose potentials and that we have an expression or a formula for the potential of a point charge, we can go ahead and do the calculation for what the potential is. There's a common factor here, right? K is a common factor. The Coulomb constant is a common factor. So I pulled it out front, 9 times 10 to the 9 Newton meters squared per Coulomb squared. And then I'm just going to multiply it by these two ratios, the first charge and its distance, and the second charge and its distance. These meters, they're naughty meters. They should be down here. Anyway, I went ahead and calculated this, and for the charge on the left, Q1, I got 257 volts is the potential at this midpoint. Is positive because it's a positive charge. For charge number 2, its potential at the midpoint is minus 154 volts. It's negative because that was a negative charge. The potential of the positive charge has a bigger size than the potential of the negative charge because it was a bigger magnitude charge, 5 nanocoulombs rather than 3 nanocoulombs. But anyway, I add these up. They partially cancel each other out. And this is the potential at the midpoint due to the superposition of the potentials of the two charges. Okay, second part of the question. So this is what I'm going to end on. What's the potential energy of this entire arrangement of charges? So this arrangement of two charges stores some electrical energy. It sort of holds some electrical energy. And one way you can calculate that electrical energy is by imagining assembling this charge distribution. And as you assemble it out of the individual charges, you total up, you add up the amount of the changes of potential energy as you bring in the first charge, as you bring in the second charge, and so on and so forth. You could apply this to multiple charges. And so that's the way I've done this. I've imagined that when I assembled this arrangement of two charges on the left and right, first I brought from far away Q1 and placed it here. And then I brought from far away Q2 and placed it here. And I calculated, firstly, the amount of energy, the change in potential energy, change in electrical potential energy when I brought in Q1. And then I calculated the change in potential energy, electrical potential energy, when I bring in Q2, the second charge over here. And I call these delta PE1, the change in electrical energy when I bring the first charge, delta PE2, the change in electrical energy when I bring in the second charge. And then I'm just going to add them up at the end to get the total change in energy. Now, actually, in this case, when you bring in the first charge, you want to calculate the change in potential energy. What you need to do is multiply the amount of charge that that charge owns by the change in potential that it just undergone. So that was a formula we met. That was the definition of electrical potential. So in this case, well, charge Q1, we know it's 5 nanocoulombs. But the change in potential, when you bring it from far away to this point here, is actually 0, because there's no other charges around at this point. So it's 5 nanocoulombs times 0, which is 0 coulombs. Now, when we get to the second charge, I've had to switch off my drawing pad because that's failing me. It's run down the power on my laptop and it was about to die. So to finish this off, I've got to go to use the mouse now. When we bring in the second charge, then we bring in the second charge into the region in the presence of the first charge. And so there we're going to multiply the second charge, here it is, second charge, by the change in voltage that it undergoes. That change in voltage is the voltage of the first charge, which we brought it into the neighborhood of. And so for the second charge, I've got to multiply its charge, minus 3 nanocoulombs, by the potential of the first charge. And that's this guy here. And so there is an energy cost to bring in that second charge. I think I can go back to my regular drawing pad. And so now we've got these two energies that we've just calculated from bringing in the first and second charges. And now we can total up those two energies. And this is the final energy of the charge arrangement. It's negative minus 3.9 times 10 to the 7 joules. The negative sign is telling us actually that because they're opposite charges, they attract one another and they like to be close to one another, and you'd have to actually put in energy, add energy to pull them apart. And so that's an example of calculating the potential energy of a charge distribution, knowing the potentials of the individual charges that make up the charge distribution. I'm going to finish there on that, just to summarize, and then I'll answer your questions in the chat. Just to summarize what we did today, we talked about energy and forces, those two perspectives, in gravity and electricity. We talked about the definition of electrical potential and paralleled it with the definition of electrical field. We talked about the relationships between fields and potentials, how to calculate the field from the potential from the field. And then we've looked at some examples involving individual point charges, a single point charge, electrical dipoles, and now collections. In this case, a 5 nanocoulomb and a minus 3 nanocoulomb charges as examples.